This video is about the theory behind the matrix chain multiplication. So let's start. Let Pn be a function that denotes the number of ways of multiplying the matrix chain which has n number of matrices. So P of 1 means we have only one matrix, and P of 1 means number of ways in which we can multiply those matrices, that is in which we can multiply one matrix. We have only one method, one way, so A1 it's 1 for, and P of 2 for two matrices we have only one method of multiplying, that is in this way, A1 then A2. And then if we have three matrices we can multiply as A1 A2 first and then with A3, else A2 A3 first and then with A1, that is 2. And then P of 4 is 5, we have seen earlier in the previous video. So suppose the matrix chain which we want to multiply is A1 A2 A3 up to An. N is some number, some natural number greater than 1. And in between at some kth position we divided. So from A1 to AK it has k number of matrices, and from k plus 1 to n it has n minus k, that is n minus k number of matrices. So for multiplying k number of matrices it will take p of k time, and for multiplying k n minus k matrices it will take p of n minus k, this much steps or number of ways. So the total number of ways for multiplying this whole series, this whole chain from A1 to An is this way, this number of these number of ways and these number of ways, where k varies from 1 to n minus 1. Because of the and this number of ways and these number of ways we have multiplied here, and k varies from 1 to n minus 1. How 1 to n minus 1? If we are dividing at kth position, so if we divide at 1, so this is one part and this much is the other part. And if and at n minus 1th position, means if we divide at this position, then this is whole one thing and then this is another thing. This should not be n, because if I will divide it by n then nothing else is left here. So we will multiply, so the value of k will be from 1 to n minus 1. This number is known as Catalan number, and let us check its validity. So P of 3, earlier we had got P of 3 will be 2. So here P of 3 means summation k equals to 1 to n minus 1, 3 minus 1 2, Q of k and P of n minus k n is 3. So it is P of 1, and it also comes, this is 1, this is also 1 1 1, so it comes as 2. Sorry, it is correct. Then for calculating this it will take 2 to the power n time complexity. How? Now this is Tn. For running the loop from 1 to n minus 1, the inside thing will get executed for n minus 1 times. Therefore n minus 1 into t of k, because here we have taken t of n, so here it will be t of k and then t of n minus k. This is a constant, this is n minus 1, t of n minus k. On solving this question we will get 2 to the power n time complexity. So we will solve this MCM algorithm by using dynamic programming approach, where we will save and use the results stored in some table named M. We have a table whose name is M, and then this is I and this is J. So Mij, any grid Mij, it will denote the minimum number of scalar multiplications required to multiply the matrices from Ai to Aj. This is very important. Mij equals to minimum number of scalar multiplications required to multiply from Ai to Aj. Here we were having from A1 to An. So if I'll tell from A30 to A50, then this is my I, this is my J from A30 to A50. So I will see the I comma J as 30 comma 50. Whatever number will be there in that grid corresponding to 30 comma 50 order pair, that grid will have the minimum number of scalar multiplications required to do the matrix chain multiplication from A30 to A50, because I am seeing at the grid 30 comma 50. And this order M will not give the required order, that is in which parenthesis or in which order shall I multiply from A30 to A50 to get the minimum number of steps, to get my work done in minimum number of steps, that we won't get here. Okay, now we have three conditions for filling this table. If I equals to j, that is the diagonal elements, if I equals to j, it means I'll be multiplying from Ai to Aj. If I equals to j, then it is only the same element Ai to Ai. It is the same matrix, only one matrix we are having. We are not, and we don't multiply the matrix with itself. So when there is only one matrix, zero scalar multiplications are required to multiply. When I is greater than j, okay, if I is greater than j, that is I is somewhere in this side and j is somewhere this side, we cannot multiply because this is not compatible. We don't know if A5 is compatible with A2, but we know A2 is compatible with A3, A3 is compatible with A4. So if I is greater than j, then the matrices will not be compatible for multiplying. Now the important, if I is less than j, that is somewhere these are the I and these are the j's, then from Ai to Aj we again take a small at kth position ak and ak plus 1. For multiplying from Ai to ak, this can be done in m of I to k. If m I comma j represents multiplying the number of steps required, minimum number of scalar multiplications for multiplying the matrices from Ai to Aj, Ik Mik will represent from Ai to Ak, what we are doing here. And then similarly Ak plus 1 to j will be this thing, number of scalar multiplications. Okay, and then ultimately this whole has to be divided with this whole, that and number of minimum number of scalar multiplications. In doing so, we will find out that we know when multiplying AB of size m cross n and n cross p, minimum number of scalar multiplications required involved in this multiplication is m into n into p, product of m and p. So similarly here also we will have two resultant matrices. Let this is R1 after multiplying these all matrices, and after multiplying these all matrices we will have R2. R1 will have the size of this Ri minus 1 into Rk, and R2 will have the size Rk cross Rj. How? Well, Ai will have the size Ri minus 1 cross Rj. How do we know this? Suppose A1, A2, A3, A4. This has the size R0, R1. A1 has the size R0 cross R1. A2 has the size R1 cross R2. A3 has the size R2 cross R3. A4 has the size R3 cross R4. Okay. And this is the input for my algorithm, this array of sizes. So the size of A1 is r 1 minus 1 is 0 and 1, 2 minus 1 is 1, 2, this is 2, 3 minus 1 and 3. So ai, if ai is my matrix, then r of I minus 1 and ri, this is my size order of the matrix. So ai will have r I minus 1 cross ri and ak will have r k minus 1 cross rk. Similarly here a k plus 1 will have r k cross k plus 1 and j will have j minus 1 cross j. So these are the sizes. And then for the resultant r1, r1 is the multiplication from ai to ak. So r1 size, the order of the r1 will be ri minus 1 and rk. This is the size of r order of r1. For r2 from ak plus 1 to aj, it will have the size rk and rj, rk cross rj. And we have to multiply r1 with r2 so that I can get this whole product. So while multiplying r1 and r2, this is r1, this is r2. While multiplying ab, number of scalar multiplications required is m n p. So here for multiplying r1 with r2, number of scalar multiplications required is r I minus 1, rk, rj, product of these three. So number of scalar multiplications for the resultant is this thing. Okay. For summing up the whole thing, for I less than j, we need these number of scalar multiplications plus these number of scalar multiplications plus these number of scalar multiplications. We have to multiply these all within themselves, these all within themselves, and then ultimately these two will result into two matrices, and for them we require this number of scalar multiplications. So this term is there, this term is there, and then this term is there. This is the minimum. We have to find the minimum number of scalar multiplications. So for finding minimum number of scalar multiplications, we have to find for which value of k we will get the minimum total of these three things. So k, what is the limit of k, or the value of k can vary from I included. If I'll include I, then it will get divided as these, and then if I'll include j, then it is not getting divided. It will get divided kth position, right? Ak will be on this side and k plus 1 on this side. If I'll divide on j, then k will it will take whole, and then this side nothing is left. So the last thing that I can take is j minus 1. So I included and j excluded. This is the condition for I is less than j. Next, in dynamic programming, we use the table for dynamic programming. This is the table M. So here for first condition was for I equals to j. For I equals to j, it is 0, the diagonal thing. For I is greater than j, I is greater than j, I is greater than j, I is greater than j. So these all, we don't have any value for this, not available. And for these things we will calculate. So while calculating or while finding out the values, we have to do this diagonally, because dynamic programming approach is used, that is the previously solved subproblem will help in finding out the new value. So to get minimum number of scalar multiplications required in the whole series of a1, a2, a3 and a4, we will see 1 to 4, because here we have told mij is minimum number of scalar multiplications required to multiply ai to aj. from A1 to A4 we will see the grid ij, that is 1 comma 4, that is this thing. And always remember, this gives the minimum number of scalar multiplication and not the order. We will see in the next video about the order and the main algorithm.